In the previous video, we took a look at being able to figure out what the graphs of three-dimensional functions look like, functions of two variables. And then we also took a look at the level curves of those functions, and we used some technology to be able to enable us to see these a little bit more accurately. We're going to take that a step further in this series of videos, and we're going to start taking a look at two applications, or I guess two principles that we've seen in calculus before. And remember, in Calculus 1, we talked about the idea of continuity, and we talked about the idea of a limit of a function in one variable. Well, we're going to take a look and extend those to the fact that we can do the same thing in two variables. So when we talk about continuity, continuity basically means that if you can substitute a point AB into a function of two variables, and that function exists, then it's continuous at that point. So in other words, what we're saying is that if AB is in the domain of that function, then it's continuous at that point AB. And so what we're looking for is we're looking at all the points AB of a function f for which the function f is continuous. So let's go ahead and find those. In these examples, we're just going to find the largest set for which the function is continuous. Essentially, what we're going to be doing is we are going to be finding the domain of these functions. So we have fxy equals ln of 2x plus 3y. Now remember, we said earlier in the previous video that with any natural log function, the interior, the composed function, or the composite part of it, has to be greater than 0. So in this case, 2x plus 3y had better be greater than 0. And so the largest set for which the domain of the function exists, or the largest set for which the function is continuous, is going to be all xy such that 2x plus 3y is greater than 0. All right. Of course, if we graphed it, we could see it very easily that this is indeed the case. A second example. We have a function fxy is equal to x minus y divided by 1 plus x squared plus y squared. We know with any rational function, the denominator cannot be equal to 0. So let's just say that 1 plus x squared plus y squared cannot be equal to 0. Or in other words, x squared plus y squared cannot be equal to negative 1. And so then we think to ourselves, well, what's the set of values for which that's true? And the set of values for which that's true is all real values of x and y. We know that anytime we square a number, the lowest it could possibly be is 0. So the smallest possible value that this could be is 0. And so since we can never reach negative 1, the domain, or the largest set for which this is going to be continuous upon, is going to be all xy in the real numbers. Okay, or we could say, another way to say that, a little bit better way, is to say such that x and y are elements of the real numbers. Technically, xy would have to be an element of R2, the two-dimensional real space. All right, so that's another way that you could say it. For those of you that are taking linear algebra or have taken linear algebra, you'll probably notice that there are multiple spaces, and R2 is certainly a space that we can work in. Now this is a rational example to which not all real numbers are going to satisfy. We know that x squared minus y cannot be equal to 0, or in other words, y cannot be equal to x squared. And so the domain for which this is continuous upon is going to be all ordered pairs xy such that x and y are real numbers, but y cannot be equal to x squared. So it can't be on that parabolic path. If for some reason we have the point like 1, 1, or 2, 4, or something like that, then unfortunately it's not going to be part of that domain. A really sneaky problem is this one, arctangent of x plus root y. And the reason it's sneaky is because, well, we have an arctangent. Let's just think back to trigonometry. And what does y equal arctan x look like? Well, this is about what it looks like. And remember, it does have horizontal asymptotes at negative pi halves and pi halves. All right. And so what does that mean? Well, that means x can be any real number. So if we extend that to 3 dimensions, well, this can be any real number so long as the interior part, the domain of the interior part is satisfied. All right, so in actuality, the arctan has nothing to do with the domain of this function because arctan has all real numbers. However, interior, we know that we can't have anything smaller than 0 for y. X can be any real number. All right, so here's our domain for this. We're going to say xy such that x, y are real numbers. However, y has to be greater than or equal to 0. So essentially, when we're looking at continuity, or the largest domain for which a function is going to be continuous, then all we have to do is we just have to look directly to the domain of the function. Now, if you recall from Calculus 1, domain was the predecessor, or continuity was the predecessor to limits. So that's what we're going to look at in the next section, is we're going to take a look at how can we identify or find the limit of a function in 2 variables.